Hey, what's up, Chem peeps? Let's do some FRQ practice for this unit. The bright line spectra observed in a spectroscope for 3 elements and a mixture of 2 of these elements are represented in the diagram below. Boom! Now, this looks a little tricky on your paper because it's in black and white, but these spectra represent the visible light spectra, and I've colored in element A just to give you an idea of some representative colors that might correspond to these wavelengths of light. Part A, state evidence from the bright line spectra that indicates element A is not present in the mixture. Okay, a couple ways you can do this, but basically, as you take a look at element A, remember that these are like fingerprints for the individual elements. They're unique to each element. And so if we don't see each of those wavelengths of light in our mixture, we know that it can't be present. So not all of the wavelengths of element A are shown in the wavelengths of the mixture. Boom. Just one way that you can answer this question, you can also get a little more specific and indicate specific wavelengths of light. For example, I know that element A has got this wavelength of light at about 700 nanometers, and that's missing from our mixture. Part B, answer the following questions related to the electron configuration of a neutral atom of zinc 64. Subpart I, determine the number of protons, neutrons, and electrons for a neutral atom of 64. Okay, I'm going to start with my protons and electrons. My number of protons is going to be equal to that atomic number for zinc. And in a neutral atom, my negative electrons are going to match the number of positive protons. So protons, 30. I'll make myself a little note here, equal to the atomic number. Electrons, also 30, is equal to the protons in a neutral atom. And then finally, the neutrons. A little trickier here. We do have a little bit of math. The number of neutrons is 34. To determine the number of neutrons, you take your mass number, which in this case is 64, and you subtract from that the atomic number, which in this case is 30. And that will give you number of neutrons. So in this case, 64 minus 30 equals our number of neutrons, 34. Kind of a throwback to the last unit. All right. Now let's get to the good stuff. All of this business about the electrons in the electron cloud and where they're located. Subpart II says write the complete orbital electron configuration for a neutral atom of zinc 64 in the ground state. We know from earlier that we've got 30 electrons that we've got to figure out where they belong in the electron cloud. I'm going to jump over to this gizmo to give you a quick refresher about how to write the orbital notation. Remember, we're going to fill the energy levels from the lowest energy level first. That's the Aufbau principle. So as I move this up to indicate where the lowest energy levels are first, I'm going to hit the first main energy level, bit 2 electrons. Then comes the second main energy level. There's a couple of sub-levels there. The first will go into the 2s, and 6 more will go into the 2p. Notice how I'm using Hund's rule to fill. And then we hit the 3s. 2 electrons go in there, and then the 3p, 6 more electrons. Things get a little hairy here. We do have the 3D sublevel, but in terms of energy, we actually are going to fill the 4s before we fill the 3D. It takes a little less energy. Again, notice how I'm using Hund's rule to fill my 3D orbitals. Boom. Now I'm just going to take a quick moment to write that out in orbital notation for you here. Whew, boom, done. The next part is going to make things a little easier for us. It's asking us to write the standard electron configuration for a neutral atom of zinc 64, but this time in the ground state. So notice what's going to happen here. I'm going to use superscripts for the number of arrows. Again, the superscripts and the arrows in each case are representing the number of electrons in that sublevel. And here's where things get a little easier, right? I jump over to 2p and there are 6 electrons in there. 3s, there are 2, 3p, there are 6, 4s, there are 2, and then 3d, there are 10. Boom, done with my standard electron configuration. Moving on to noble gas, going to make my life even easier. We need to figure out which noble gas precedes zinc. So if I look at my periodic table, zinc is here. The noble gas that directly precedes it with a complete valence level is argon. So I'm going to put argon in brackets and then pick up where argon leaves off after 3p6. We'll go 4s2, 3d10. Woo! Now we're moving. So part 5. Write one possible excited state electron configuration for a neutral atom of zinc-64. You may use orbital, standard, or noble gas notation. Okay, I'm going to stick with noble gas notation because that one's my favorite, makes my life the easiest. And know that there are a lot of possibilities here. An excited state is just going to have the electrons in higher energy orbitals than what they would be in the ground state. And there's lots of different possibilities. I'm going to take just one electron from my 4s orbital. So instead of 4s2, I'm write 4s1. And I'm going to say that it hops and skips all the way past the 3D orbitals and all the way up to the 4p orbital. So notice that I still have the same total number of electrons. It's still a neutral atom of zinc, but I'm just showing you one example of how one of those electrons has moved up to a higher energy orbital than it would otherwise occupy. There's lots of options here that you can come up with. This is just one example. All right, let's do some math. Part C says the emission spectrum indicates neutral atoms of zinc-64 emit photons of light with a wavelength of 700 decimal point per sig figs nanometers. Show a numerical setup and calculate the energy of a single photon of light in joules per photon. Now notice that is underlined that the zinc-64 atoms emit. All right, so as we think about solving this, we need to recognize that calculating the energy of a single photon is given by the equation that we have on our formula chart. Planck's constant times the speed of light divided by the wavelength in meters. And so as I think about this, much of this information is coming from my formula chart and not something that I have to remember. Planck's constant, 6.63 times 10 to the minus 34 joules times seconds, times my speed of light, which is 3.00 times 10 to the 8 meters per second. Again, meters per second is letting me know or reminding me that my wavelength has to be in meters in order to make this math work. And so notice that my wavelength is originally given to me in nanometers. So I have to first take that 700 nanometers and convert it to meters, remembering, of course, that 1 meter is a billion or 1 times 10 to the 9 nanometers. And so this same wavelength in meters, taking my 700 nanometers and essentially multiplying by 1 and divided by a billion, is going to give me my wavelength in meters 7.00 times 10 to the minus 7 meters. So I'll take that and plug it in to my equation for the energy of a photon. And when I solve this, I get the energy of just one individual photon with a wavelength of 700 nanometers. So Planck's constant, notice how I'm putting it in parentheses, times the speed of light, again, locking it in its own parentheses here, enter, divide by my wavelength in meters. Again, another number in scientific notation that I'm putting in a parentheses for us here. Boom. And so the energy to just three significant figures is going to be 2.84 times 10 to the minus 19 joules per photon. It's a really tiny number, right? But that's the amount of energy carried by just one single photon. That's where the second part comes in. Show a numerical setup and calculate the energy of 1 mole of photons in kilojoules per mole. Again, I'm going to pay very careful attention to what it's asking me to solve for here. I'm going to take my amount of energy that I've just calculated in terms of joules per photon, and notice what I do here with my units. This is the amount of energy in joules per one single photon. Right? And now, as I set this up to solve, I'm going to use the power of dimensional analysis. I know that I need kilojoules, so I'm going to convert from kilojoules to joules, recognizing that there are 1,000 joules in 1 kilojoule. And then here's where things might get a little wild. Notice I'm going to put photons on the top and I'm going to put moles on the bottom. 1 mole of anything, in this case photons, Avogadro's number of things. 6.02 times 10 to the 23. And the power of dimensional analysis is it allows you to really see how those units cancel out. The photon bit, I think, is a little challenging here, right? Because it started on the bottom and now we're canceling it out with something on the top. Notice we're left with kilojoules per mole. I'm just going to jump to my good friend calculator to solve this, right? First, essentially, I multiply by 1, so times 1, divide by 1,000, and then I multiply by Avogadro's number. Again, notice how I'm putting this in a parentheses. That'll save you. Boom. So in kilojoules per mole of photons to 3 significant figures, 171 kilojoules per mole. Boom. We are done.